Yes.
Right. Okay, okay. ठीक है. Thank you. So the plan of the lecture is to revise the Kelvin-Planck statement of second law of thermodynamics, which was discussed yesterday. That is one of the idea. The second is we would be discussing the concept of refrigerator and a heat pump. The reason is, if you want to appreciate the second law of thermodynamics, the second statement of second law of thermodynamics. Sorry. So the idea is to revise the Kelvin-Planck statement number 1, okay, till the others join, okay, and then let me just close this. We would be discussing the concept of refrigerator and a heat pump. The reason of discussing refrigerator and heat pump is to make sure that you understand the second statement properly, the second statement of second law of thermodynamics, namely the Clausius statement of second law of thermodynamics. Okay, so just as we need idea about what is a heat engine to appreciate the Kelvin-Planck statement, the concept of perpetual motion machine of the second kind to appreciate the Kelvin-Planck statement of second law of thermodynamics. Similarly, we need to be sure that we understand what the Clausius statement has to say. So the Clausius statement has to do with a device which is called as, and all of you have seen that device, a very common device in your households, called as a refrigerator. But it could be any other device which is a refrigeration system. It could be a large capacity cold storage plant doing the refrigeration exercise, or it could be your window air conditioner also. Okay, so we are not going to study much constructional details about that. We would be looking at it from the block diagram level or from the conceptual level. Okay, just as we had seen the heat engine. So that is the idea of the lecture today. Okay, before we begin, I want to make sure that you understood the concept of heat engine, and for that I would be running a poll first. This is to make sure that you understood the concept of heat engine. Okay, so let us launch the poll and let us see what you are answering. The question is very clear. I am asking you about the heat engine. You have spent considerable time on the heat engine concept. This should also tell me whether you have really understood the Kelvin-Planck statement of second law, without which you won't be, it's not possible for us to go to the second statement. So I am asking you in this question, what is the correct description of a heat engine? Okay, there are three options given to you. One is that whether it converts the entire amount of heat to work, whether it converts the work transferred to heat, or whether it converts partially the heat to work. Okay, so these are the three options in front of you, and from your responses I would be in a position to grasp whether you are really understanding the heat engine concept, as well as what the second law of thermodynamics, especially the KP statement, the Kelvin-Planck statement, has to tell. Okay, so the responses which we are getting, they are not very encouraging. About 70% of the students are getting it right, but then 30% are not getting it right. It means that they are not followed it. So the question is clear that what is the heat engine? What is the heat? What the heat engine does? Whether it converts the heat to work entirely, whether it converts work to heat, or whether it partially converts heat to work. That is, these are the three options given to you. So let me close the poll and let me show you the responses. So the responses are, you see that 20% are saying that the heat engine converts the entire amount of heat supplied to work. 16% are saying that it converts the work transferred to the heat engine to heat, and about 64% are saying that partially, there's a partial conversion, not the total conversion of heat to work. So the option obviously is the third answer is correct, that is heat engine partially converts heat to work. It is not that it converts the entire amount of heat to work, and that is what the Kelvin Planck statement was about. Okay, so if you see that, I'll just draw the heat engine diagram again, which Professor Murukar had drawn, the block diagram, not the sorry. Okay, so this block diagram you need to be comfortable with now. Let us call this as engine, E for engine. And what this is we are supplying some heat, let us say Q in or Q supplied, whatever you want to use notation, in the heat engine. As was discussed yesterday, the heat is being supplied from certain source which is at certain higher temperature, TH or whatever, and this heat engine would partially convert the heat to work, while rejecting certain heat. So this rejected heat always needs to be greater than zero. It cannot be zero. So this is the description of heat engine. Okay, this is the same I am drawing. So the Kelvin Planck statement is saying that the Kelvin Planck statement says that the heat engine would always reject certain heat. We cannot design a heat engine. We cannot think of a heat engine. Even if we cannot think of a heat engine which is going to convert the entire amount of heat to work. So it is not possible. It is not possible to have this efficiency according to Kelvin Planck statement. Please note that it is not possible to have a heat engine whose efficiency is 100% according to Kelvin Planck statement. Okay, Kelvin Planck statement. So the point I am trying to make is, in order to understand the Kelvin Planck statement, we need to be comfortable with the concept of heat engine. In order to understand the Kelvin Planck statement of second law, okay, to appreciate what it tells us, we need to be comfortable with the concept of the heat engine. And what is a heat engine? We said it is a conversion device. It converts the heat to work and not work to heat, as some people have understood, answered. Okay, it is not converting the work to heat, it is converting the heat to work, and it does not convert the entire amount of heat to work. It only partially converts the heat to work. How much it converts? It would depend upon the efficiency of the engine. This we should be very clear about the heat engine. Okay, so if your concept of heat engine is clear, now I would explain you another concept which is required for you to understand the next statement, which is the Clausius statement of second law. Okay, please note the spelling of this person, Rudolf Clausius. Okay, who contributed a lot in providing insights to number of concepts of thermodynamics. So, named after him is the Clausius statement of second law, which I am going to tell you. But before telling you that statement, before explaining that statement, I would be explaining you the concept of refrigerator. Okay, concept of refrigerator. So again, first I will be drawing a diagram of a block diagram as I had drawn of an engine. So next to it, in order to appreciate uh, this concept, I'll first draw the block diagram, and then I would draw a schematic of a refrigerator. A schematic of a refrigerator. All of you have seen a refrigerator, okay, or what is in the popular language is known as fridge. So I would just refer to R as a refrigeration system. Okay, and what this refrigeration system does is, look at the block diagram and look at how it is different from the diagram of the block diagram of the heat engine. Okay, so this block diagram you should be very careful while drawing. Look at the direction of the arrows which I am drawing, and how these arrows come, that I would explain you with when I am going to explain you what is a constructional I am drawing. Okay, wherein I am showing again a sink and a source. I am showing a sink and a source. The sink is at certain temperature TL, a lower temperature TL. So this we can consider as a lower temperature reservoir, which is a TL, and this is a higher temperature reservoir TH. And what later doing is that it is transferring the heat. Look at this. It is transferring the heat from a lower temperature body. This is the lower temperature reservoir to a higher temperature reservoir. To a higher temperature reservoir. And for transferring this heat from a lower temperature body to a higher temperature body, it cannot happen spontaneously. We need to supply certain work. Okay, so some work is being supplied. Some work is being supplied to this refrigerator for performing this role. Which role it performs? It is basically transferring this heat from a lower temperature body. Now, if you want to understand this with reference to your household refrigerator, okay, this system, this block diagram, if you want to understand with reference to the household refrigerator, so let me erase this heat engine now. So look at this. I am rubbing this, erasing this heat engine block diagram, which I hope you must have internalized. And now we are going to move on. Okay, so you must always have in mind the refrigerator. Not considering why we are understanding what is the refrigeration system, because I want you to understand the Clausius statement of second law, which has to do in a way with the refrigeration system. Okay, so you know that we have all seen a refrigerator, and you know that in the freezer section of the refrigerator, you are getting the cooling effect. You are getting the cooling effect. Okay, and if you want to list down the components of, if you want to list the components of the refrigeration system, then let me list down the components. So one component is what is known as the freezer or evaporator. So you know that there are basically four basic components of any refrigeration system. So one is the evaporator. So in your household refrigerator, this evaporator is in the freezer section. There is a freezer section in your household refrigerator. So that portion is the evaporator. Okay. So there is one heat exchanger called as evaporator. Then there is a component which is consuming electricity. There is a component which is consuming electricity, and unfortunately, because that is why we are getting the electricity bill. So that component which consumes the electricity of your household refrigerator is the compressor. So the second component, major component of the refrigeration system is the compressor. Then you have another heat exchanger, which is, if you in the old model, you would find that if it's the old model of refrigerator, you can always look at the back side of the refrigerator and you'll find that there is a heat exchanger there that is generally coated with black, and it's provided with fins, and it is called as a condenser. In the modern refrigerators, you will find that it is concealed, so you won't be able to locate that easily. Okay, so that is a condenser. So this is the third component of major component of your refrigeration system. And the fourth is what is known as some expansion device. Okay, so in your household refrigerator, you would often find that there is known as a capillary tube, which functions, which performs the function of expansion. And that is, there are a number of other expansion devices, but we are not taking the refrigeration course now, so that in detail you will be studying when you take up the refrigeration air conditioning course. Now what you need to simply understand is, these are the four components. Which are the four components of a refrigeration system? Evaporator, compressor, condenser, and expansion device. And if they are connected in a particular order, they would perform a thermodynamic cycle. Okay, so now I am going to connect them in a definite order. Okay, for that again I would rub this, erase this. Okay, and I am now going to draw a block diagram. Okay, in order for us to appreciate what happens in the household refrigerator, or for that matter any refrigeration system, including your air conditioning system. Okay, because air conditioning system also has all these four components which I had mentioned. Okay, all these four components you will find in your window AC also, in your split AC also. Okay, even in larger systems you would have expansion walls and the components which I had mentioned. Okay, now this block diagram, okay, this schematic rather, I will be drawing. Let me choose another color for this. Okay, so as I said, there are four components. There are two heat exchangers. And we need to appreciate not the details of this heat exchanger, because that is a separate course of design of heat exchanger in your heat transfer. Now what we are going to appreciate from a thermodynamic angle is the direction of the heat transfer. Okay, so this is a heat exchanger, the evaporator. This is the heat exchanger, the evaporator. Okay, and there is another heat exchanger which is condenser. There is another heat exchanger, namely the condenser. Okay, so the working fluid in the refrigeration system is known as a refrigerant. So what happens is, in the evaporator there is a transfer of heat from the space to be cooled. For example, if this is your space where you are storing your vegetables or whatever, okay, some goods which are to be preserved, okay, goods to be preserved. Okay, so what you need to do is that you need to lower the temperature of this space, right? You need to lower the temperature of this space, and in order to lower the temperature of this space, we need to extract certain heat from this. So that heat is QL. So this QL which I had drawn here, okay, is this QL. This QL is this QL, and this would correspond to approximately the evaporator temperature. Okay, why I'm saying approximately, that you would understand later when you take up the course of refrigeration and air conditioning. So I don't want to confuse you a lot here. So I would say that this evaporator is approximately at a temperature TL. Okay, and it would maintain the space. At this temperature TL. Okay, lower temperature TL. Okay, there has to be some temperature difference in order for the heat transfer to happen. Okay, but now we will assume that heat transfer happens through an infinite, simply small temperature difference. Okay, very small temperature difference. So this is QL. Now what happens is, this refrigerant goes to another device which is a compressor, and this refrigerant is compressed so that its temperature increases. And for compressing it, and it increases to, let us say, TH. Okay, let us say okay. And for doing this, look at this diagram. The block diagram, and look at this diagram over here. We need to supply certain work. So this work which I have drawn here, this is the compression work. So in the schematic, you see that this is the compression work which is drawn here. It is a compression work which would pump the heat from a lower temperature, that is TL, and it would take the heat. And transfer it over here, which is QH. Okay. So this is QL, which is being taken. This heat, while condensation is being rejected, and this heat is ultimately transferred to the surroundings, the environment. This is thrown to the surrounding. Okay, so if you touch the condenser of your household refrigerator, you will find that it is hot. And it is at the temperature TH. Okay, it is at the temperature TH. If you put your hand in the freezer section of your household refrigerator, you will feel that is at a temperature TL. A lower temperature TL. Okay, and then finally, what is happening is you need to expand it back to the evaporator pressure. So this is a thermodynamic cycle. Okay, this is a thermodynamic cycle. So this system performs a thermodynamic cycle. Why it performs a thermodynamic cycle? For example, initially the refrigerant was as a state 1, then it goes to a state 2, okay, after compression. Then the refrigerant is condensed to a liquid which is a state 3, and then it is expanded to a state 4. Then again it goes to the evaporator and come back to the state 1. So this would repeat. State 1 to state 2, state 2 to state 3, state 3 to state 4, back to state 1. So this is it means that the working fluid, that is the refrigerant in this case, is performing a thermodynamic cycle. So this refrigerant would perform a thermodynamic cycle, which I have now included in the block diagram also. Now, in order to achieve this, what is happening is, if you look at this, the heat which was QL, okay, is being transferred from a temperature TL. This is being transferred from a temperature TL to a higher temperature TH. Okay. So this QL gets transferred from a lower temperature to a higher temperature, and in order to achieve this heat transfer from a lower temperature TH to a higher temperature, lower temperature TL to a higher temperature TH, we need to supply certain work which is greater than zero. And this device is called as a refrigerator. Okay, I'm trying to be very brief. Actually, it's very conceptual and interesting system, but I don't want to lose my focus on the broader aspect of this, which has to do with the Clausius statement. Okay, so that is the reason why I'm making this discussion very brief. I'm not going into much detail. So now what we need to appreciate is that this refrigerator device, what it does is that it is pumping the heat from a lower temperature to a higher temperature, and for pumping this, it is consuming certain work. Now, what this second law statement says, what the Clausius statement is about, is, it is saying that, okay, going into that I'm not interested right now. I'm trying to tell you what is the meaning of that statement, what it is trying to tell you. This Clausius statement of second law of thermodynamics tells you that if you want to pump the heat from the lower temperature reservoir, that is TL, let us say at TL, to a higher temperature reservoir TH, then we cannot do that without expending any work. Means we cannot have a system like this where WC is 0. If WC is equal to 0, if the compressor work is equal to 0, okay, or if the work transfer rather talking it as compressor work transfer is 0, then that system is not possible. In nature, we cannot have this kind of which work temperature body input without any work input. So this is one way of expressing the Clausius statement. Okay, so I hope that is clear what is a Clausius statement. We'll repeat the statement again, but I want to make sure that you are understanding what I'm discussing. So the poll question is seen. What is the correct description of a refrigerator? Okay, I'm asking a very simple question based on the discussion which I am having. What is the correct description of a refrigerator? What the refrigerator does? So the students are still confused based on the responses. If you are giving the responses after listening to what I have discussed, okay, then I need to repeat this, I guess. Akanksha Salunke, can you hear me? Akanksha Salunke, unmute yourself.
Sir, I believe mobile they don't have option of unmuting. It can be done only if they are using laptop or
Okay, all right. If few of them are using laptop, they might be in a position to answer. Okay.
Yeah.
All right. But if we make them panelists, they would answer, I guess.
No, still if they are using mobile, they can't do, I believe. Because in questions,
is that so?
Last time we have made them panelists, but still they are not able to answer.
Okay, all right. So there is a confusion here that about 50% of the students have understood the concept of this is from whatever you have answered in the poll, assuming that you are listening to the lecture and answering the polls after listening to the lecture. Okay. So assuming this, 50% of the class I understood what is the concept of a refrigerator. Okay. Let me repeat it again. That a refrigerator transfers the heat from a lower temperature body to a higher temperature body. A refrigerator would transfer the heat from a lower temperature body to a higher temperature body. It is not that it is transferring the heat
Sir, you are not audible, sir. Hello, Shelar, sir.
Hello, am I audible now? Okay, there were some issues of the audio, I guess. So I logged in again.
Yes, now you are audible, sir.
Yeah, okay. There were some issues of the connectivity. So there is some spelling mistake. Clausius spelling is Clausius. Okay. So Clausius statement of second law of thermodynamics. What it tells you is heat cannot be heat cannot be pumped from a lower temperature to higher temperature without any work input. We need to supply certain work. Okay, for example, in your household refrigerator, what we are doing is that we are taking the heat from the freezer section. We are taking that heat and we are throwing it out to the surrounding. Now freezer section is at a lower temperature. No, freezer is at a lower temperature. What does the refrigerator do? It takes the heat from the freezer section. Freezer section is at a lower temperature. The approximate temperature in the freezer is about -4 degrees centigrade. And the ambient temperature is surrounding temperature is around 25 degrees centigrade. So what does the refrigerator do? It takes the heat from the freezer section, which is at -5 degrees centigrade, and it throws that heat to the surrounding outside. It throws that heat to the surrounding, which is outside, which is at a higher temperature at 25 degrees centigrade. Now, how this happens? This happens because you are supplying electricity to the compressor. If your compressor is shut down, or if you are switching off the switch which supplies electricity to the compressor, this phenomena would not happen. Okay, so the fridge would operate and it would cool the freezer only if your compressor is on. So what is the meaning of compressor is on? In thermodynamics, the meaning of compressor is on is you are supplying certain work. So if you are supplying certain work, then and then that refrigerator can pump the heat from a lower temperature to higher temperature. So the correct answer is, I'm closing the poll and sharing the answer. So the correct answer is the heat can be pumped from a lower temperature to higher temperature, but we need to supply certain work. So the Clausius statement is, please check the spelling of Clausius, Clausius, not Dius, as it's incorrectly typed there. So Clausius statement says that you can pump the heat from a lower temperature to a higher temperature, For that, we need to supply certain work. Please note this, okay? And then we'll come to, I'll share my screen now. The last concept I'll come to before we stop this. This concept has to do with, is the whiteboard visible? Is the whiteboard visible?
Yes, sir, it is visible.
Okay. So now we'll forget about the schematic, which is a bit complicated. Okay, so we'll stick to the block diagram. Okay, we'll stick to the block diagram of our refrigerator. Okay, so let me rub this first. Now what I'm going to tell you is that how do you capture the performance of this? Okay, so the performance of this machine, a refrigerator, is captured by a parameter called as, please note, COP. C stands for coefficient, O stands for off, and P stands for performance. So if you want to talk about the performance of refrigeration system, then we need to define what is called as COP, and that COP, if you look at the diagram, that COP for a refrigerator is the cooling effect or the refrigerating effect, that is the refrigerating effect, QL, upon the input to this machine. So the output of this machine, please note that the output of the refrigerator is the desired output of the refrigerator is the cooling effect. Why are we purchasing refrigerator in the market? The desired effect or the output of the refrigerator, the desired effect or the output of the refrigerator is the output of the refrigerator is the cooling effect. It is the cooling effect. This is QL is the output, and input to this machine is the work, the electricity which we supply. So the input to this machine is the work, the electricity which we supply, and the output of this machine is the cooling effect, that is QL. So QL upon W is called as coefficient of performance for a refrigerator. Okay, for a refrigeration system, please note that the performance is captured by coefficient of performance. For an engine, we talk about efficiency. For a refrigerator, we talk about coefficient of performance. Now, what is the difference between these two? The difference is efficiency. When you are talking about the efficiency of the engine, okay, when you talk about efficiency, we talk about the engine. The efficiency of the engine, we talk about converting the heat to work. We are talking about converting this heat to work. How much of the heat we are able to convert it to work, that is called as the efficiency. Okay, how much of the heat we are able to convert to work is called as the efficiency. Coefficient of performance is not about conversion. It is not about conversion. We are not talking about conversion efficiency here. We are talking about how much cooling effect or how much cooling effect we get by supplying certain work, and how much of this heat can be pumped, by supplying certain work. So we need more and more heat to be removed, or more and more refrigerating effect, by supplying minimum work. That is the objective of designing a refrigerator. So the coefficient of performance of a refrigerator is QL upon W. Okay, let me ask you this question and we'll end with this. Okay, let me ask you one question. Hopefully you would be in a position to answer this. Coefficient of performance of a refrigerator. So from your responses, I can conclude that most of you have understood this concept of coefficient of performance, okay, of a refrigerator. We will be revising this concept. Even if you have not understood this, even if you have not understood the Clausius statement of second law in much detail, we would be again spending one more hour in exploring this concept. Professor Murukar would join us tomorrow, and we would have a revision of this, whatever has been taught today. I thought that I would also cover heat pump, but because the time is too short, okay, so I guess that couldn't have given the justice to this concept of heat pump. So let me sum up what we have discussed. What we have discussed is how is the heat engine different from a refrigerator? Number one, what we have discussed is how is the heat engine different from a refrigerator, component wise also and conceptually also. Conceptually, how it is different? Conceptually, a heat engine converts the heat to work, whereas the refrigerator does not convert heat to work. What it does is, a refrigerator would pump the heat from a lower temperature body to a higher temperature body. That is the difference, essential difference, conceptual difference. We are also looked into constructional aspects of heat engine and refrigerator. We said that a heat engine essentially would have a prime mover like a turbine, for example, or an engine proper, which would convert the heat to work. Okay, whereas in your refrigeration system you would have essentially heat exchangers like evaporator and condenser, and we would have some devices for changing the pressure like compressor and expansion devices. Okay, so that is what we are seeing. Then we have looked into the Clausius statement of second law, which talks about the impossibility of constructing a device which would pump the heat from a lower temperature to a higher temperature without any work input. So what the Clausius statement says us is, it is not possible for us to construct a refrigerator which will not consume any electricity. Okay, what is the Clausius statement? It tells you that you cannot construct a refrigerator which would not consume any electricity. So if you want to construct a refrigerator which pumps the heat from a lower temperature to a higher temperature, then we should be expending certain work. So in your household refrigerator, that work is expended in your compressor of the refrigerator. So the compressor is a component where you are giving certain work so that there is a pumping of heat from a lower temperature to higher temperature. Okay, I hope that one more concept at the end we had discussed, which is called as a coefficient of performance. So coefficient of performance is what? Coefficient of performance is a way of capturing the performance of refrigerating machine, and it is different from efficiency because it is not talking about a conversion efficiency. We are not talking about conversion efficiency here. So coefficient of performance is basically talking about how much cooling effect a refrigerator gives you. How much cooling effect a refrigerator gives you, that is QL, upon the work input to that machine. So QL upon W is the coefficient of performance of a refrigerating machine. I hope whatever concepts we have discussed that you must have followed. Even if you have not followed those, okay, because of some connectivity issues, okay, we would again revisit those concepts in more detail in the next class. Thank you very much for joining.
Thank you, sir.
Yeah. Close the pool. Okay, 87% of you have understood this, and I'm ending the webinar.